Hey there, BC Calculus kids, second semester. Isn't this going to be fun? Happy snow days. Here I am recording from the dining room of my house, so all the noise that you hear in the background will just be normal family activity. Fun, fun, fun. Devin is giving me such a sneering face right now. Anyway, I'm not weird. So just a little overview of second semester. Unit 7 is what we're going to start with, differential equations and logistic growth. Students generally find this unit not so bad, especially at the beginning. Unit 8, applications of integration, has a lot of artistic pieces to it. Again, kids seem to like this unit as well. The end part gets a little nasty, and before that, the nasty part is when AB ends. So if you've taken AB calculus before now, about 3/4 of the way through Unit 8 is where your course stopped. So the end of applications of integration, and then Unit 9 and 10 are all brand new topics. There is a couple of new topics inside Unit 7 that are BC only, but not as many, obviously, as in Unit 9 and Unit 10. So again, students generally like Unit 7 okay, like Unit 8 okay. Series and sequences generally makes kids cry. I don't even know why sequences is on there. It really just is series. So hopefully you have some notes from your pre-cal class when you did series, and look that up because we'll be doing that same math and then adding a calculus component to it. Vectors and polar calculus, kids are just, it's not terribly difficult, but it's very, very algebraic, just like series is. And kids are tired at this point. We're usually rushing because of snow days and field trips and spring break and all that kind of stuff will crunch our time. And this is Unit 10 and the series pieces, why you need honors pre-cal or IB pre-cal HL, because the algebraic pieces that are built into these units are covered in that course and they're not in the on-level pre-cal. So your second semester grades, Unit 7 and 8 tests will be on third quarter, Unit 9 and Unit 10 tests will be on fourth quarter. We will have assignments and assessments in the review for AP exam time. There will be grades, and we will be finished with all the grades before the AP exam. There won't be any grades after that, but the amount of points available to you are going to be the same amount of points that are available in the other quarters. Also, you'll be getting next year's recommendations. You're going to have to sign up if you're a senior. You can tune out right now, but you're going to sign up for courses next year. Multivariable and differential equations is one choice, although they are semester courses. For instance, if you want to take differential equations second semester, you do not have to take multivariable first semester. They are not dependent upon one another. It is fairly natural for most kids to transition from multivariable to differential equations, but it is not required. IBHL is a full year course ending in an IB exam, but you don't have to take the IB exam. The only thing you have to do is be a senior to be in that class. Even if you haven't been a magnet kid before, if you're interested in IBHL and you are a senior, you're eligible to take that class. Logic and linear algebra are new to us. Logic, again, is a first semester course, and linear algebra is a second semester course. They're not dependent upon one another, so if you want to take linear algebra, you can. You don't have to take logic first semester. Or if you took multivariable first semester and you want to take linear algebra second semester, that's fine. So multivariable, differential equation, logic, and linear algebra, you can mix and match those. Multivariable and differential equations, though, is the most rigorous algebraically, which is why you're not going to be recommended for it unless you have an 80% average in BC. And if you haven't taken BC, you are not eligible to take multivariable and differential equations. However, logic and linear algebra don't require as much algebraic manipulation. It's not as high as multivariable and differential equations, so that's why you have only the 70%. And students who have taken AB only and not BC can take logic and linear algebra, where they cannot take multivariable. You had to have taken BC calculus with an 80% to get into multivariable and differential equations. AB students can take logic or linear algebra. And then, of course, many of you have already taken AP statistics, but if you haven't, you can take that concurrently with any of these. And you only need Algebra 2, have finished Algebra 2 to be able to take AP statistics. Also, some of these, there are students that take multivariable, differential equations, and higher level. Like, all of these can be taken. You could fill your dance card, if you will, with all math classes.
What?
Devin liked that analogy. Any questions? See your teacher. All right, so let's move on. So, Unit 7, initial value problems, and here is your homework assignment. It is in your textbook. And again, there is a video from your textbook posted on Edline that goes along with this if you want to watch that. We have chosen to break up some of the first sections of this book into a couple of different lessons. So, a little review. Remember, if you have a simple two-variable equation, then you can take its derivative with respect to x, and you get a slope-generating function. Of course, if you have the same parabola shifted up or down, you know that the derivative is the same. Regardless of where that parabola is shifted up or down, the slopes at any particular x are still the same. Except when we try to go backwards, we learned at the end of first semester that if you are just given the derivative, only given, 2x, to get back to x squared plus 3 or x squared minus 5 is difficult. That's why we add the plus c, saying, look, we don't know exactly what the vertical shift is, but we know that there could have been one, even if it was 0. Well, now, as long as I have an initial value condition, I can indeed find out what the exact function was given a derivative. So notice that this time, given the derivative and a point on the original, dagger, x comma y, and in this case 1 comma 4. A little annoying that they give you the y first, right? I anti-differentiate both sides, technically, right? You have an equation, so I can take the antiderivative of this side and the antiderivative of this side. The antiderivative of a derivative is just y. The antiderivative of 2x, of course, is the power up rule, plus c. But then I'm going to plug in my initial condition. This is the x when y, not y prime, when y was 4. So I take the 4, and put it right there. And the x, and put it right there. And then I can do simple algebra 1. Solve for c and I get 3. So now I have not just a rando family of functions. I've got the particular solution because I was given an initial condition. So this is sometimes called an initial value problem because you are given the initial value along with the derivative. Now what's kind of cool, what are you doing?
Just checking out the video.
Yeah? What are you doing? Anyhow, an equation containing a derivative is called a differential equation. So notice this green box up here? This is a differential equation. So you are solving differential equations in Calc BC calculus. Even in AB calculus, you will solve differential equations. When you take the course differential equations, of course, you will solve much more difficult differential equations.
Much more difficult.
Oh my gosh. Chippies.
I didn't do
So,
anything.
yeah, you were the total orchestrator of that. So here's an example 1. Solve the following first order. Here's what first order means. First order means that the derivative I'm going to give you is just y prime, not y double prime or triple prime or anything like that. So I bet you can guess what a second order differential equation would be. A. So there's a derivative. This time notice I used the dy dx notation instead of the y prime. Still, I'm going to anti-differentiate both sides with respect to x. And get y is equal to e to the x minus 2x cubed plus c. Plug in the initial condition. This time they gave me the x first. Right? As soon as I get this, I say to myself the x was 1 and the y was 0. And I plug them in. I solved for c. And then I wrote my final result. Notice again that if I just take the derivative of this, well, gee, what is y prime? Y prime is e to the x minus 6x squared, which is what I started with. Wish I could take a video right now of Devin dancing. Oh, she finished her Chem IA, yay! So example 2, look how clever I am. Example 2 uses a second order differential equation, which means I need 2 initial values. So notice that this is when y of 0 means when x is 0, y is 1. This one, though, is when x is 0, y prime is 0. So when I take, there's the example. Here's my example. I'm going to anti-differentiate both sides with respect to x. But notice when I anti-differentiate the second derivative, I get the first derivative. Plug in first derivative information. Solve for c. Not my final answer, because when you are supposed to solve, inherent in the word solve a differential equation means you get back to y. Not. Notice here I haven't gotten back to y. I haven't gotten y by itself. Look, that's same pre-algebra. Get y by itself. Y right now is surrounded by a second derivative. Y surrounded by a first derivative. Undo it. Start again. Notice I've already used this information. Now I'm going to say anti-differentiate both sides, get y by itself, plus c. Now use 0, 1 to solve for c. This is now my final answer. I have solved because I have y by itself. Yay! Word problem. So, a rocket is fired straight up from a platform 3 meters above the ground with an initial velocity of 160 meters per second. Assume that the only force affecting the rocket during its flight is from gravity, which produces a constant downward acceleration of 9.8 meters per second squared. Notice on the previous examples I didn't have any units. That's because they didn't give me any units. This problem has units with it, so I need to make sure that I use units on my final answer. They gave me t is equal to 0 when the projectile is fired. Find a formula for. Now notice here they're asking me not for a velocity value but a velocity function. and then they're asking me for a height function. Remember in first semester, we did PVA, position to velocity to acceleration. Notice that in this problem, they really gave me a function for acceleration. I agree it's a little bit unfair to have you recognize these words as an acceleration function, but now that I've told you, it's not unfair anymore. So, notice I've underlined things in blue that go with position. This is the position of the rocket. 3 meters above the ground at time equals 0. In red, I have velocity information. Initial velocity of 160 meters per second. So, the second derivative of position. Position typically for some unknown reason is referred to with the letter S. Second derivative of position is acceleration. Acceleration is constantly negative 9.8. Downward 9.8. Right? Negative, down, 9.8, given. So, I need to find the height and the velocity. Given acceleration, take the antiderivative to get to velocity. So there's the velocity plus c. Plus c, I should be able to have an initial condition. When t is equal to 0, what was my initial velocity? Oh, right here. So I plugged in 160 at time 0 and got my velocity. This is, velocity is the first derivative of position. So I have answered part A. Here is the velocity. To get the height, I need to take the antiderivative of position, because the antiderivative of position, of velocity, is position. So there's me getting the antiderivative plus c, and then using the initial condition that at t is equal to 0, the rocket is 3 meters above the ground. And there's me plugging that in, and getting the height of the rocket above the ground as a function of time. Yay. So, given all of this, you should be able to do the homework assignments given at the first of this slide. Hey, hi! Look, can you see my beret? Our French friends sent 5 berets to us for Christmas. They just came in the mail today. So we have 2 blue and 3 pink, and we're all wearing them around today. Now I'm going to go to... Ah! Sorry, did that hurt? I fell down. I'm going to go to the next day. So the second day would have had this warm-up. There's the composition book reminder that for those of you that are in my class this semester that weren't in my class first semester, Mr. Chase and Mr. Davis may or may not have done warm-up books. I forget. One does and one doesn't. But for me, you have a warm-up book with the warm-ups written, the words, the math, and the correct answer, and then I check them usually once per unit and give you some fluffy points for it. The announcement for AP1 being tomorrow, obviously, the AP problem, the first AP problem is on first semester topics, not anything we've done here. And I don't know what tomorrow is. Well, I mean, I do know what tomorrow is, but I don't know if we'll be in school tomorrow. And if we are in school tomorrow, the first day back, I wouldn't give you an AP, but expect AP1 soon. So anyway, here's our warm-up. Let's do our warm-up together. So I've given you acceleration. Here's the acceleration. Here's how I know this is an initial value problem, is they have a velocity initial condition, right, time 0, and a position time 0. They've asking me to solve a second order, and again, with the word solve means I have to get all the way back, no derivatives, right? The acceleration is a derivative. This is a differential equation. It is the second derivative of position. So when I take the antiderivative of both sides, I will get v of t is equal to the antiderivative of 3e to the t, which is also 3e to the t, minus power up plus c. Since this is velocity, I need to import the initial velocity condition and say that 6 is equal to 3e to the 0 minus 0, right, plus c. But don't forget, 3e to the 0 is not 0. E to the 0 is 1. So this is 6 is equal to 3 plus c. Therefore, c is equal to 3. So my final answer, velocity, given the initial, silly me, is 3e to the t minus t to the 5th over 5 plus c. But I'm only halfway done. I've used this one. So now I am going to take the antiderivative of velocity, which will give me position. The antiderivative of 3e to the t is still 3e to the t minus power up over the 6 times the 5 that's already there, plus the antiderivative of 3 is not 0. The antiderivative of 3 would be 3t plus c. Now import the initial position condition, which is negative 5 is equal to 3e to the 0 minus 0 plus 0 plus c. So again, this is going to turn into 1 to e to the 0 is 1, 1 times 3 is 3, subtract 3 from both sides, and I get negative 8 is equal to c. So my final answer is that. There you go. All right. So, given a closed interval, 0 to 3, what is the velocity of a particle when its acceleration is at a maximum? So this seems to be, we're taking a little bit of a turn here from initial value. And asking you about velocity but when its acceleration is at a max. So, in calculus, kids, in calculus, somebody asks you about a maximum, you need to think about the first derivative. Calculus. Any function has a potential max at endpoints, right? Closed interval, and when its derivative is equal to 0 or does not exist, and changes from positive to negative. This is the most important part. You have to show and know that when a derivative changes sign is when the original function has either a max or a min, if it's on the interior of the domain. So I have my calculator, and I'm going to give you the warm-up function. So notice that in y1, in my calculator, in y1, I have velocity. No, dummy, that's not velocity, right? If I go back, what is that one? 3e to the t minus t to the fourth, that's acceleration, right? Oh, check that out. This is acceleration. Now I did put the velocity in here as 1, but notice that what I'm taking the derivative of. What am I graphing the derivative of? I'm graphing the derivative of what's in y1. So what am I looking at? Here I have endpoints and where the derivative of velocity, right? The derivative of velocity is acceleration. So I'm looking at a derivative, right? Which again, I could have just, I could have, since this derivative was easy to find, I could have graphed y2. The only reason I'm doing this is to, if I wouldn't bother taking a derivative if I had my calculator. I just already had the derivative from the warm-up. But I don't need this if I have my calculator. I can just put in acceleration and then graph its derivative. So here's the derivative. Where's the derivative? The derivative endpoint. What is true about the derivative? The derivative is positive from the left endpoint, which means you're increasing, therefore this endpoint is a min. Over here, this right endpoint, the derivative is negative, and if the derivative is negative, the original function is decreasing to the right endpoint. This is also a min. However, here, the derivative is equal to 0. The derivative of acceleration, being velocity, is 0. And changes from positive to negative, therefore here is a max. So on my calculator, I found the 0. Then on my home screen, I second quit to my home screen, and I plugged into y2 that x value. So what am I doing there? If I'm plugging into y2, I'm plugging into velocity. Of course, I could have done that to y3 too, remember, because that is also the velocity. But I plugged in the x, and the nice thing about you can do x or alpha x here, is that it keeps all of the decimal places, because AP always says you need to maintain all the decimal places that you're plugging in until your final answer, then round. So, what is the velocity of the particle when its acceleration is at a maximum? So over here I found the x coordinate where the derivative is at a max. The derivative is at a max, this x. Then I took that x and put it into the velocity function because this asked me what is the velocity. Whoops, sorry. So my answer is velocity is 14.892 meters per second when acceleration is at max. Now, if this is multiple choice, you don't go through all this nonsense. But if this is a free response question and somebody asks you about a maximum of I don't care, you somehow talk about looking at its derivative for where its derivative change signs. And I know the acceleration is accelerated a maximum because acceleration's derivative changed from positive to negative at x equals 1.495. All right, for the same function, at a different time, is the particle speeding up or slowing down? This we also talked about in our PVA unit. If velocity and acceleration have the same sign, then you think of the particle as going faster. Two forces acting in the same direction. If either force is operating in the opposite direction, then that's going to have a slowing down effect. And that's all AP. Now, Mr. Getz would yell at me for calling these things forces, blah, 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 blah. All AP cares about is that you can state either one of those things as a justification. So again, I'm using my calculator. In y1 and y2, I have acceleration and velocity. So I plugged in 6.5 into acceleration, plugged in 6.5 into velocity. Don't care about all of those digits. And I'm going to say, because acceleration at t equals 6.5 is positive, velocity at t equals 6.5 is negative, therefore particle slowing down. Done and done. Now, distance versus displacement. Distance versus displacement is how we've also talked about this in Unit 5 when we talked about collecting integral values that are positive versus changing signs. What does that mean? So if I want you to find the position of a particle at any time t, now we're moving from the warm-up function, I'm giving you a new velocity function. This velocity function is quadratic. Find the position of the particle at any time. That tells me I need a function to find the position of the particle, and here's my initial, so here's where we're linking up initial condition or initial value. If I'm given velocity. So, anti-differentiate both sides, and I can go from velocity to position. Power up, over 3, 3's cancel out, isn't that convenient? Minus t squared, power up, so that would be over 2, the 2's cancel out, isn't that convenient? Minus t plus c. Then to bring in my initial condition, right, when t equals 0, all these t's are going to go out, so hopefully without too much work you can see, without me showing my work, you can see that this would be 3, right, because I would be plugging in a 0 for these. So find the position of a particle at any time. There you go. Oop, my bad. What is the particle's position at t equals 3? 3 cubed is usually 27, minus 3 squared, which is 9, minus 3 plus 3, those would cancel out. 27 minus 9 is usually 18, right? Did they give me any units? No, unitless. What's up, Dill?
Are you sure recording?
Yep.
Hello!
Silly kid. Now, what if I asked you what is the displacement of the particle from 0 to 3? So again, look here, find the position at 3. Position was 18. So where is the position at 3 seconds? It is at 18. What is the displacement from 0 to 3, though, versus what is the total distance traveled by the particle from 0 to 3? Well, here's a graph of the quadratic velocity function from 0 to 3. Notice that velocity is negative from 0 to that x-intercept, and then is positive from that x-intercept after. So if you integrate from 0 to 3, you're going to integrate integrate and sum some negative values and positive values. Remember, the units on a velocity, even though this silly problem didn't have any units, but remember, this is v of t units, and this is t units. So when you anti-differentiate, you're multiplying per time, you know, units per time times time, so that's why you get position out of that. So if you integrate from 0 to 3, right, if you have a calculator, you just math 9 this. If you don't have a calculator, this is easy enough to anti-differentiate. Plug in 3, plug in 0, and you'll get 18, which is what the position at 3, minus, right, minus 3. That's the displacement. So you get 15, whatever units are on here. Note to self, add units to this problem. But if we want total distance traveled, right? I don't care whether you went up, down, right, or left. I just want to know total distance. I need those negative velocity values to be turned positive. So notice that I've written two integrals and that I have an unknown upper limit here and an unknown lower limit. What do you think that is? There's a reason why you spend time in Algebra 1, Algebra 2, and Pre-Cal finding x-intercepts, right? This is a quadratic. If I have a calculator, well, whatever. I'm not going to need it anyway for reasons I'll show you in a second. Maybe you already figured it out. But if I don't have a calculator, I need to know that x-intercept. Can you freaking do Algebra 1 and factor this? I hope, I hope, I hope. Right? What am I going to get here? So I'm going to solve this for 2t's, and I'm going to get t is equal to negative, right? This is going to give me my negative x-intercept, which I don't care about. But this, t minus 1 is equal to 0, therefore t is equal to 1. So this x-intercept is 1, 0. So the 1 goes here and here. And notice then, I'm taking the opposite of the integral from 0 to 1, which will take all these negative integral values and turn them positive, you know, and then we'll negate it. And then I will just add the rest of the positive integral values from 1 to 3. I'm going to get more than 15, right? So I'm taking, again, if I didn't have a calculator, I take the opposite of second fundamental theorem plus second fundamental theorem, and I get 17 units, right, which is more than the 15 displacement units, because displacement just wants to know where did you end up. So let's pretend this is a left-right issue. So after time equals 0, the particle was going left, then turned around and went right. So ended up, right, travel, you know, the displacement is 15, displacement from start, right, 15 units from start, because this particle went left 3 units, then right. Got it? But here, if I want to know the total distance traveled, I need to negate the negative units and combine them with the positive units to get 17 units total distance traveled, regardless of right, left, up, down. Now, if I had my calculator, I don't need to find the x-intercept, because if I have my calculator and I want distance, I will just take not the absolute value of the whole thing, but I will take the absolute value of velocity and take this graph and make it look like this. Ooh, that's terrible. Right? That's what the absolute value graph would look like. And then integrate from 0 to 3, and I've got all positive values. And you know how to do that in your calculator. That's what the older software looks like, where you use f and n, absolute value of y1 with respect to x from 0 to 3. No need for x-intercepts, no need for factoring. I just get 17 out of that. Notice that is not the same as if you took the absolute value. If you had done the absolute value of the integral, you would still get 15, right? Because the calculator would integrate, get displacement, absolute value it, and still give you 15. You would not get distance unless you absolute value the velocity function before integrating. So here is a handout that is on Edline. There is 3 handouts, distance and displacement 1, 2, and 3. So I'm going to do distance and displacement 1 and 2 with you, and then 3 is your homework, along with that book homework from the first lesson. So, Willis cruising down his neighborhood street, realizes he's not done his calculus homework. In a panic to get home quickly and do his homework, Willis accelerates his car, giving it a velocity, blah, blah, blah. Notice units, feet per second, after he started accelerating. Find the times at which the velocity is equal to 0. Note, this is, when they do this, this is supposed to help you. You like when they ask you this. So I took my velocity function, set it equal to 0. I can't tell you how many times, not because you're dumb, but for speed, I will get kids when they see t to the 1/2 is equal to 2, I'll get t is equal to radical 1/2 instead of squaring both sides, right? Silly kids. Right? You are squaring here. So this is an x-intercept. Note to self, x-intercept on velocity. No calculus there, algebra. Now, find his net displacement for the time interval 1 to 9. Find his net displacement means I'm going to end up with a number, not a function, right? They're actually asking for his displacement. His displacement means I don't care about positive or negative, I just need to integrate from 1 to 9. Okay? So I integrated velocity. The antiderivative is power up, 2/3 t to the 3/2 minus 2t from 1 to 9. Use my second fundamental theorem. And of course, if I have my calculator, I just math 9 this. And I get 103rd. Notice the units feet, because with velocity is feet per second times seconds, which is why I get feet out of this. The next question is find the total distance he travels from the time interval 1 to 9. Here's where I need to know total distance means that I have to have all positive integral values. And I know from the problem up here that there is an x-intercept on the velocity function where the velocity function hits the x-axis. Now I need to see if it changes sign there. And indeed, I know that t to the 1, because I know this is the square root function and I took algebra 2 and paid attention, that this function at 0 is -2 square root, and I just found the x-intercept, which is at 4, 0, and that this function ends at, what, 9 something. What is 9? Square root of 9 is 3, 3 minus 2 is 1. So I'm negating the negative velocity values, which are from 1 to 4. Notice it did start me at 1, even though I started my graph at 0. That was just because of habit of looking at that y-intercept. But they asked me to start at 1. So I negated the integral values from 1 to 4, and then I added the positive values from 4 to 9. If I had a calculator, I would just do this, which, right, so this would be non-calc, and this would be calculator. Whichever way, if you have your, either way, you have to show the setup, right? The answer meant 1 point. You've got to show this. If you don't have a calculator, this is the setup. If you do have a calculator, they'll accept either one, unless they specifically say don't use absolute value, which sadly they do sometimes. All right, number 2. A particle moves along the x-axis, acceleration, time equals 1, velocity, initial condition on acceleration, initial condition on velocity, and it's initial condition position. Find a velocity function. So unlike the Willis problem, they're asking me not for a number but for a function. So I anti-differentiated plus c, plugged in my initial condition, and ended up with my velocity function because c ended up to be 0. Right, velocity function, again, anti-differentiate acceleration to get a velocity plus c. This is velocity plus c. So I went to my velocity initial condition that at 1, plugging in 1, velocity was -2. Now I've used that one. So there's my velocity. Find the position function. Again, they're asking me for a function, not a number. So I anti-differentiated velocity to get position plus c. Then I used my initial condition. At 1, position was 0, so there's 0, and here's me plugging in 1, and I got my position function. C says find the total displacement. So since I'm finding displacement, I'm actually going to come up with a number. Note I'm going from 1 to 8. So I'm going to integrate 1 to 8. Don't care if positive and negative, doesn't matter. I just want total displacement. Also units. 3 places at least past the decimal. Oops, sorry. Oh, this got cut off. Find the total distance the particle travels. So the total distance, if I have my calculator, which I would for this, I can tell, you know, with as nasty numbers as these are, from 1 to 8. Answer in feet. Got cut off, so I don't see what my answer is right off the bat. But the solutions will be online. Alright, distance and displacement 2. An object moving in a straight line has a velocity of that, feet per second. Find the time sum intervals in which the velocity is positive and which it is negative. Again, this, if they're going to ask me this, I know this is going to help me later. So, factor that quadratic. That quadratic opens up, has a y-intercept of 16. So, factored it nicely, got my 2 x-intercepts. I know a parabola that opens up and has 2 x-intercept is going to be positive on the left and the right of the x-intercepts and negative in between. Find the total distance means I need to negate what's happening. So going from 0 to 2, I need to negate any negative. So going from 0 to 2, this function was positive, so I could just integrate velocity, just use my calculator. But then I negated integrating from 2 to 6, because from 2 to 6, that's where, is that 2 to 6 or 2 to 8? What is that? Oh, 2 to 6, right, on each one of these intervals. Again, if you have your calculator, you can also just do absolute value. But sometimes AP will say, show the setup without absolute value. So here you can see this. Use a single integral to find the displacement in the time given interval, and use a single integral to find the distance traveled. So going from 0 to 6, displacement, don't care about positive or negative. A single interval to do distance, I would need to absolute value. Show how the answers in part C can be found from what I did before. Right, so that's me showing displacement and then just negating the negative part to get distance. Find the acceleration of the object at the midpoint of this interval. So, acceleration, take velocity. Right, I need the derivative of velocity, gives me acceleration. 2t minus 10, plug in 3, which is the midpoint of 0 to 6. Units. Number 2, take a moment to appreciate this humor. Runs out of gas as she is driving up a long hill. She lets the car roll, blah, blah, blah. Velocity. Here. Units. What is the car's net displacement between the times 10 and 40? Displacement, don't care whether you're positive or negative, so I just did the antiderivative of velocity. Antiderivative rule was very easy to find. 10 to 40, plugged in, got my answer, and units. Total distance. Without my calculator, I would need to know the x-intercept, which goes all the way back. Oh no, it doesn't, sorry, that was number 1. I would need to recognize from here that I would have to find the x-intercept of this linear function. Oh, that's so hard. Not. So 10 to 30 minus 30 to 40, right? It's a linear function with a negative slope. So it would be positive before the x-intercept and negative after the x-intercept, which is why you need to negate the second one. Number 3 asks about the graph, reading a graph below. So just looking at this graph with areas, right? These are areas, not integral values. So what is the displacement of the article? From 0 to c, displacement would be the integral, right? Just the integral of v of t. So the integral from 0 to a would be 3, the same as the area, but not from a to b. The integral from a to b is not 5. The integral would be negative 5. And then again, the integral from b to c would be positive. But the distance would be the absolute value of the integral. So this 5, which was negative, would become positive. Approximately where does the particle achieve its greatest positive acceleration on the interval 0 to b? Where is the steepest positive slope, right? Slope is derivative, and acceleration is the derivative of velocity. So I thought it approximately here was the steepest one. It was right at the end point. Approximately where does the particle achieve its greatest positive acceleration on the interval to 0 to c? Wasn't sure why this question was. Seems to me to be the same, right? All right, so there we go. An hour approximately for these 2 lessons. And remember, there are 2 homework assignments that go with it. There is the book homework assignment that goes with initial value, And then the third handout, distance and displacement number 3, which you can get on Edline. I will also have the solutions up there for you to look at. And so are these PowerPoints just without the video component are also up on Edline. So again, go out and have fun in the snow. That's what we're doing. We've built a snowman. We've done some snowboarding. And we've had plenty of snowball fights. So I'm hoping that you do the same, have some fun, but also do some calculus. And we'll see what happens with the next snow day predictions. Do you think we'll be in school at all this week? I'm not sure. So I may be back. Anyway, see you later. Bye.